Welcome to the deep dive. Now, for anyone working in physics, the speed of light, see, it's just fundamental, right? But measuring its speed just one way, turns out that's way trickier than you might think.
It really is. We can measure the round-trip speed incredibly accurately, bounce light off a mirror, time it, no problem. But isolating that trip just there, or just back, that opens up a whole can of worms, theoretically speaking.
And today we're diving into one specific, maybe less conventional approach to this problem.
That's right. We're looking at quantum geometry dynamics, or QGD. It's laid out in this document, Quantum Geometry Dynamics, an axiomatic approach to physics. And the first big thing you need to grasp is that QGD starts from a really different place than, say, relativity.
How so?
Well, instead of assuming space-time is this smooth, continuous sheet, QGD says no, space itself is fundamentally discrete. It's made of tiny fundamental units.
Okay, like pixels instead of a perfect photograph.
Sorta, yeah. And it bases its physics on that idea, using fundamental particles it calls preons, plus, and preons. It's an axiomatic approach.
And this different starting point, this discrete space, allows QGD to propose a way to actually measure the one-way speed of light.
Exactly. That's what we're focusing on today, digging into how QGD suggests we could tackle this measurement. This is really aimed at those of you listening with a physics background, maybe interested in, alternative ways of thinking about these foundational questions.
Right, so let's get into that discrete space idea first. QGD says it's fundamental. The document even mentions a theorem, something about Euclidean space emerging from this quantum space.
Ah, yes, the theorem on the emergence of Euclidean space from quantum geometrical space. Basically, QGD argues that the familiar, smooth, continuous Euclidean geometry we all use, Pythagoras, all that isn't the fundamental reality.
It's an approximation.
Precisely. It's what emerges when you look at this discrete quantum geometrical space from far enough away,
Yeah.
at larger scales. Think of a TV screen. Up close, you see the individual pixels, right? Red, green, blue dots. But step back, and your brain smooths it all out into a continuous image. QGD suggests space is similar. The fundamental units, the preons, are the pixels. Our macroscopic world is the smoothed-out picture where Euclidean geometry works remarkably well, but it's an emergent property, not the underlying structure.
Okay, preons are space units, and you mentioned preons plus.
Right. Preons plus are associated with matter and energy. And this distinction leads to a really key concept in QGD, especially for our topic today, the difference between intrinsic velocity and metric velocity.
Okay, let's break that down. Intrinsic versus metric velocity. What's the difference?
So intrinsic velocity in QGD is described as a frame-independent property. It's defined by a particle's momentum divided by its mass. And importantly, mass in QGD is essentially the number of preons plus making up the particle.
Frame independent, so it doesn't matter who's measuring it.
That's the idea for intrinsic velocity, yes. And for a photon, QGD states its intrinsic velocity, let's call it via gamma, is equal to its momentum over its mass, gamma, which equals c.
Speed of light.
But here, c is interpreted as the fundamental speed limit related to the preons plus themselves, how fast they can interact or propagate within this discrete structure. It's an inherent property of the QGD universe.
Okay, so that's intrinsic velocity. What about metric velocity then?
Metric velocity is what we'd normally call velocity, the one we measure in experiments. Distance traveled divided by the time it took, measured by our clocks, relative to our specific frame of reference.
Like tracking a car with a stopwatch and a known distance?
Exactly. And QGD is very clear. This metric velocity is related to the intrinsic velocity. It's proportional, but it's not the same thing. Our own motion relative to that underlying quantum geometrical space can affect the metric velocity we actually measure.
Ah, okay. So QGD says the intrinsic speed of light is constant and isotropic, the same in all directions, because it's tied to this fundamental preon plus speed c.
Correct. That intrinsic c is a true constant in their framework.
But then it predicts that the metric speed of light, the one we try to measure going one way, might not be isotropic. It could be different depending on the direction we measure it in.
That's the crucial prediction, yes. The potential anisotropy, the direction dependence, comes into play when we talk about the measured metric speed.
Why? If the underlying speed is the same everywhere.
It boils down to the measurement process itself. Our clocks, our rulers, our entire reference frame might be moving relative to this fundamental discrete space. QGD suggests this relative motion, and crucially how we synchronize our clocks over a distance influences the time interval we measure for light to travel a certain distance. So even if the intrinsic speed is isotropic, The measured delta t could vary with direction.
Okay, that makes sense. The measurement itself introduces potential dependencies. This leads us straight to the experiment QGD proposes. How do they suggest we actually measure this?
Right. The document outlines a setup. It's conceptually pretty straightforward, actually, building on classic ideas. You have two clocks, clock A and clock B.
Synchronized clocks.
Synchronized, yes, and placed a known distance, Dellers apart. First, you send a light signal from A to B. Clock B records the time interval it took, let's call it delta T, A right R,
I
of
get
B.
it.
Then you do the reverse. Send a signal from B to A. Clock A records that time interval, delta TB right R A.
And then you just calculate the speeds?
Pretty much. The one-way speed from A to B would be C right RO, and from B to A, it's C left RO D delta TB.
But wait, the synchronization, that's always the catch with one-way speed measurements, isn't it? How does QGD handle synchronizing A and B accurately enough? Einstein synchronization itself assumes the one-way speed is C.
Absolutely, that's the core difficulty, and QGD acknowledges it directly. They don't rely on the standard Einstein synchronization convention for this specific purpose because that convention defines the one-way speed to be C.
So what do they propose?
They propose a practical, iterative synchronization procedure. It involves sending signals back and forth between the clocks and adjusting their times based on those signals. The idea is to repeat this process until the clocks are deemed synchronized, effectively compensating for any time dilation effects predicted by both relativity and QGD due to their relative state.
An iterative process. The goal is to get synchronization that's independent of assumptions about the one-way speed itself as much as possible.
That seems to be the aim, yes, to establish a synchronization state suitable for testing the one-way speed rather than defining it.
Okay, let's assume they can achieve this practical synchronization. What's the big deal if this experiment finds that psi isn't the same as left-out, or if they're different from the known two-way speed, psi left-right or own?
Well, first, QGD predicts the two-way metric speed, C left right or own, will equal the fundamental speed C. But if the one-way speeds, C left or own, are measured to be different from each other or different from C, that would be huge.
Why huge?
Because it would directly support QGD's core idea. The theory predicts exactly this possibility, that the metric one-way speed can be anisotropic, influenced by the motion of the observer's reference frame relative to the underlying quantum geometrical space.
So finding right arrow and axis left arrow would be evidence for this hidden motion, this movement relative to the discrete space.
Yes, it would imply that our measurements are indeed sensitive to our velocity through this fundamental structure. The difference between right arrow and left arrow, or their deviation from C, could potentially be used to calculate the metric velocity of our lab frame relative to that structure.
And that's, well, it sounds like finding an absolute velocity, something relative to space itself.
That's exactly what QGD suggests. If you can accurately measure an anisotropic one-way speed of light, it provides a way, within their framework, to determine the absolute metric velocity of any object relative to the quantum geometrical space.
Which is, of course, a massive departure from special relativity.
A fundamental departure. Special relativity's second postulate is the constancy of the speed of light in all inertial frames. This implies that, with proper synchronization like Einstein's method, the one-way speed must be isotropic and equal to the two-way speed, c. Detecting an absolute velocity is deemed impossible within SR.
So SR says you can't measure absolute motion, and the one-way speed is always c by definition postulate, if synchronized correctly. QGD says maybe space is discrete, which distinguishes intrinsic and metric speed, and maybe we can measure an anisotropic one-way metric speed, which would reveal our absolute motion relative to that discrete space.
That's a very good summary of the core contrast on this point. QGD, by starting with discrete space and differentiating these velocity types, opens a theoretical door that SR closes. It proposes a concrete experimental test.
A test with potentially revolutionary implications. If QGD's prediction holds, finding a variable one-way speed wouldn't just be a curiosity, it would challenge the foundations of how we understand space-time, wouldn't it?
Absolutely. It would lend significant weight to QGD's discrete space model and the concept of a preferred reference frame associated with that space. It fundamentally alters the geometrical picture of our universe assumed by relativity.
So let's just pause on that. It really gives you something to think about. Imagine this experiment is done, refined, repeated, and the results consistently show an anisotropy in the one-way speed of light fitting QGD's predictions.
What would that mean for physics? It's a profound question. How would we reconcile that with the decades of success relativity has had?
It forces you, especially if you're working in physics, to consider what a theory based on fundamentally discrete units rather than a continuum would look like. Not just for light, but what about gravity, quantum fields, cosmology?
That's a whole different paradigm, a potentially radical shift.
Definitely food for thought. And if you want to explore QGD's ideas in more detail, including its axioms and other predictions, the source we've been discussing is the document Quantum Geometry Dynamics, an axiomatic approach to physics.
It lays out their full framework.
Well, that brings us to the end of this particular deep dive. Thanks for joining us.